Hello everyone, welcome to my demo. This is Abdulaziz Al-Maslouf from University of California Riverside, and I will be presenting DLEEL multi-predicate spatial queries on user-generated streaming data. First, social media platforms make it possible to all users to post their data constantly at any time from anywhere. For example, Twitter has 330 million active users per month, and they generate 500 million tweets per day. Facebook even has bigger than that, 2.4 billion users, and they generate 3.2 billion likes and comments every day. And there is other social media platform. And this data has been explored, used, analyzed, and mined to serve different applications from business, science, health, and even politics. So real-time applications that rely on user-generated data are increasing in number and importance. For example, there are systems that utilize this user-generated data to make recommendations for users, and there are even systems to find event detections based on social and community. And actually now people use this user-generated to find real local time news instead of the media, the mainstreaming media. There is social media search, and there's system to improve the disaster management. So basically, we are focusing on two broad queries. First, temporal Geo-Social queries and temporal spatial keywords queries, and both these queries on streaming data. So what makes streaming data different than traditional data? First, the time sensitivity. So whenever I submit a query right now, they submit the same query within seconds or minutes, most likely I will get different answers. Another difference is the amount of data that comes to the system is tremendously huge. We are talking about millions of objects per second on these streaming data, streaming systems. Okay, first, Geo-Social Queries. The Geo-Social Queries are getting popular and everywhere with increasing user-generated social platforms. And a major category of Geo-Social Queries is spatial personalized search. And this is beyond a single search for all users. This is a tailored search that's specialized for every single users. And this is actually now supported by top-notch systems such as Facebook, Instagram, and Twitter. An example of that is find top K tweets, K equals 10, posted recently by my social network in downtown Chicago. As you can see here, there's 3 dimensions: time, social, and space. Problem overview. I have a data set where each object in this data represents with a triple: user ID, location, and time. And I'm studying these queries on 2 fundamental queries: range query and KNN. Example for range query: find the most recent K tweets, K equals 20, posted by my friends and friends of my friends, and spatially located within Bahamas. So range query ranks the object based on timestamps, and KNN example for that is find recent K tweets, K equals 10, posted by my friends and friends of my friends, and especially near to downtown Chicago. And KNN ranks the objects based on combination of 2 different scores, the spatial and temporal, as you can see here. And both these scores normalized by maximum range and maximum time. Here's an overview on the indexing. Basically, I have on the main memory that index the streaming data, the most recent. And there's in-memory buffer, and the third component, which is on the disk, social graph index. Why we store social graph index in the disk? Because it's a huge in number and size, and it's not going to accommodate on the main memory. And this is the in-memory buffer to get data from the social graph back and forth. And if we get closer to in-memory data index, basically it's a quadtree that's extended with the user awareness. So as you can see here in the leaf nodes, there is a user's IDs, and each user points to their post IDs. And these post IDs order based on the timestamps. And the insertion on this index is done by batch insertion to cope up with such high rates, insertion rates. And in this social index, I have this social network. I can easily convert this to this list. Every users point to their friends, and I can store them on disk. And now, Geo-Social Query process overview. Basically, the user will submit a query. Then the query processor will retrieve the spatial cells, and then we'll retrieve the user friends, either from main memory or the disk. Then we're going to get the objects, the key object, by applying social, spatial, and temporal pruning. And if we get the key object, we are done. If not, we're going to expand to the next level and we're going to loop until we get key objects. Now, temporal spatial keyword queries. Spatial keyword queries are so popular and everywhere. A prominent example for that, point of interest search, which is supported by top-notch systems such as Google, Facebook, and Twitter. There's a new search, route planning, and social media search. And just more recently, spatial keywords query made it to system-level support, which is actually a huge step for this kind of query. Now we have Tornado, Asterisk, TP, Kite, all incorporate this kind of query on their systems. Example of these systems, or this query, sorry. I have these keywords for Michael, and I have this space in Florida, Panama City Beach. I'm trying to find the tweets that on this location and has these keywords. Problem overview, I have a data set D, where each object in this data set presents with a triple location, keyword, time. And again, I'm setting this query on two fundamental queries, range query and KNN. Example for range query, find the most recent K tweet, K equal 20, that mentions safe or help, and spatially located within Panama City Beach, Florida. And for KNN, example for that, find recent K tweet, K equal 3, that mentions Hurricane Michael, and spatially near to 6th Street. Range query ranks again the object based on the timestamps, and KNN, similar to Geo-Social Queries, rank the objects based on combination of spatial and temporal, both normalized by maximum range and maximum time. Now indexing framework. So I have two main categories, pure indices and hyper indices. The pure indices, either indexing space or the keywords, the first three here, just for space, grid, quad tree, R tree, and the inverse index is just for keywords. And if we combine these together, we're going to get space first, then keyword second, grid inverted, quad inverted, R tree inverted. And if we do the opposites, we're going to get the keyword first, space second, we get inverted grids, inverted quads, inverted R tree. And we are studying these indices from systems perspective to see the loss and gain if we employ one indices or other on the context of streaming data. Now let's go to the demo. So basically have this. First, we're going to do the Geo-Social Queries. They have this location. Let's select Dallas, for example. And they have these social users. I'm going to select one of these. Let's do range query. And the maximum range, let's say 20. And let's get the top 10. So this spatial distance weight is not applicable for range query. It's just for KNN. Let's hit search. So now we get this kind of objects that is related to the user to be social network. As you can see here is order based on timestamp, the most recent first, and the second most recent, third most recent. And if we switch to the other query KNN, so we are going to use the spatial distance weight, which is either you select between space and time. Here we are in the middle. As you can see here, we get these objects from this user social network. And this is kind of in the middle, is not basically for, we didn't put weight on space or time in the middle. If we put more on space, we're going to get the object all based on their distance. And if we switch to the other side, which is going to put more weight on the time. As you can see here, time, the most important. And now we're going to switch to the other queries, which is geotextual query. Again, we are in Dallas, Texas. Let's select this location and let's search for coffee break. Let's do range query first, maximum 20 miles, and let's say 10, top 10, and let's search. Now we get these objects based on these keywords and the space on this within 20 miles. And again, this object rank based on timestamps, as you can see here. If we switch to the KNN, and now in the middle between space and time, as you can see here, the combination between time and space. And if we switch all the way to just space, we're going to get the closer, the next, the further. And if we switch all the way to the time, we're going to get this object based on time. So basically here, space is 0 and time is 1. And here in the middle. That's pretty much about my demo. Thank you for watching.